So hello everyone. Well, I'm happy to host our first joint mutual and MML Learning Online Workshop. My name is Taras Podinets. I'm representing Geothermal Ukraine among the GoSyn project. Today we have our main topic of our event is sustainable heating and cooling solution for industrial and district heating. And the event is organized by GeoSyn project in collaboration with GeoCluster Partners projects. A few words about the event. The workshop is organized collaboration with such projects like GeoStackis, GeoFlex Heat, FlexGeo, Treasure, Hawk Loop, uses for heat, Interstores, Urgent, Cool Life, and Rewitch as a part of GeoCluster initiative. This event is aiming to foster the knowledge sharing, cross-project collaboration, and mutual learning with a strong focus on innovative, sustainable heating and cooling solution for industrial application and district heating. The key thematical focus includes geothermal energy, thermal energy storage, advanced heat pumps technologies, and their policy and marketing integration pathways. The workshop forms part of the broader efforts to accelerate the deployment of the clean heat solution across Europe and to support the decarbonization of energy system in line with EU climate goals. For the time being, we've organized our event with the next schedule. We have 12 speakers from 11 projects. Each speaker will have 10 minutes of presentation, and in the end of the presentation, we will have the Q&A session. So let's start with the first thematical session. The topic is the geothermal innovation and advanced thermal energy storage for industrial decarbonization. I'm pleased to introduce the first speaker, Lorenzo Talluri, PhD and researcher from the University of Florence, Italy, with the topic from Project GeoSyn, from Earth to Industry, Geothermal Solutions for Sustainable Heating and Cooling. Lorenzo, the floor is yours.
Okay, thank you very much, Taras, for the nice introduction. I will then start with my presentation. Okay. So, good morning, everyone. I will talk about this discussion on GeoSyn project. So, from heart to industry, geothermal solution for sustainable heating and cooling. Particularly during this presentation, I will try to provide an overview of the GeoSyn project, why it is interesting to have the implementation of geothermal energy within heating and cooling needs industrial sector. I will show you the solution. So the high temperature heat pump and injector cycle working with water as working fluid, showing you the case studies and trying to draw some conclusions. First of all, it is interesting to underline that almost 1/5 of the European provinces exhibit suitable geothermal condition for medium temperature applications, so in providing heat for industries. Obviously, this kind of heat is not suitable for all of the thermal needs, but there are some technologies that could improve this heat and provide it at the right temperature for the integration of industrial processes, such as high temperature heat pumps. And indeed, this kind of solution could be economically viable if coupled with new technologies for geothermal exploitation. So we can estimate that the industrial demand could be partly be satisfied by this kind of solutions. And there are lots of industrial potential that could be exploited. Particularly, we can see in the literature lots of works like the one from Wolf and Blesch or Kosmadakis and Marina that estimate the picojoules of energy consumption from thermal processes lower than 100 degrees Celsius or in the range between 100 and 200 degrees Celsius, which are the one that could be directly sourced by geothermal energy or upgraded thanks to a high temperature heat pump. Indeed, there could be a nice sector coupling between geothermal energy and industrial processes. Particularly, there are lots of industries such as paper, food and beverages, chemicals that requires temperature between 80 to 200 degrees Celsius. And this could allow the utilization of high temperature heat pumps or normal heat pumps as key technology for the enabling of next generation and fossil fuel decarbonization. So this kind of issue is what we want to try to solve, or at least to think, in GeoSyn project. GeoSyn project aim is to develop an integrated solution that harness the geothermal energy. Particularly, we have got a geothermal source at about 120 degrees Celsius and upgraded it with a high temperature heat pump and also provide cooling for chilling at about 12 degrees Celsius. Indeed, in lots of industrial applications, there is the need both of heat for thermal processes and cool. For example, in the agri-food, it is very well widespread, the requirement for both heat and cold. So we are, as UniFi, are the scientific coordinator of the project and WFUP leader of the thermal design of the system, and we are trying to coordinate this innovation within GeoSyn. What we have proposed is indeed these two technologies that should work, that could either work singularly or simultaneously in order to increase the use of the cascade energy of geothermal energy. GeoSyn project partners are these ones, so from APRE, Geothermal Ukraine, COSVIG, University of Florence, Ribacol, NeoEco, SDU, and SINTEF. And this small consortium is very goal-oriented in order to provide an effective solution. The most innovative part of GeoSyn project is the benefit of using water as the working fluid. Why water? Because water is the most natural working fluid, no GWP 0, ODP 0, and no PFAS issues. It's not toxic, non flammable, and it is very highly cost effective. Moreover, it has a very high potential because, for example, the latent heat of condensation at 25 degrees Celsius is 14 times higher compared to R134A. Obviously, not all of the sparkle is gold, and there are some issues with water, and specifically the high specific heat ratio, the very high specific volume of steam, and the normal boiling point of 100 degrees Celsius. These characteristics bring to the issues that need to be solved of high discharge temperature at the compressor exit, the high volumetric flow rates, and the compression ratios, especially if we go with the temperature at the evaporator lower than 100 degrees Celsius, which will mean going subatmospheric condition. So what we needed was to try to have a flexible configuration where we have at the condenser a temperature of about 120 degrees Celsius, and indeed we have got steam entering the cheese factory, which is the case studies between 130 degrees Celsius. We already have placed a monitoring system at the demo site, and so we know the condition of temperature and pressure. The goal was to develop a heat pump with a condenser duty of 50 kilowatts, a temperature lift of at least 80 Kelvin, and the supply steam temperature at least 180-200 degrees Celsius. And thanks to these constraints, what we obtained is a collaboration with Officine Mario Dorin that are developing a reciprocating piston compressor for this project and also for the twin projects Geostekis. And this compressor will have 4 stages of compression. And then the solution implemented. There will be a high temperature heat pump with 4 stages. And then we have got the condenser, an internal heat exchangers, and the evaporator. And then we have got also receiver for the flexibility of the system. We can see that with this solution, we could reach, at least theoretically, a coefficient of performance from a temperature lift of 80 Kelvin from 120 to 200 degrees Celsius of 3.6, which is well above the target that we set during the proposal writing. This is just a piece of geosyn. The other piece is about the ejector cycle, which is still innovative and still using water as working fluid. Then we provided a thermodynamic modeling with several configurations and also provided a computational fluid dynamic analysis for the ejector that we will be designing and building completely anew for the geosyn project. Thanks to the calculation of this kind of plant, we will implement this kind of solution. So an evaporator where there will be the direct injection of the water. There are two cycles, motor cycles, let's say, where the heat is the water is converted in steam and then provided to the ejector, and then the refrigeration cycle, which is this part where the cooled part will go to the case studies, basically speaking. So we have got this kind of cycle, one which is close to a motorcycle and one which is a refrigeration cycle. The effective coefficient of performance of this kind of solution is of about 0.5, which is a quite good solution if we think about heat-powered refrigeration systems. And then we have got the case studies. We've got a real case studies, which is the San Martino dairy factory, which is this one, which is very close to the Enel Green Power plant, Nuova San Martino. And then we have got a steam pipeline that provides heat directly to the cheese factory. And then we will be able to upgrade this heat and downgrade it to cooling requirements through the innovative geosyn solutions. Furthermore, thanks to the work of all of the consortium, we also found several case studies where the application of the high temperature heat pump, but also for the cooling system, could be exploited, like in the food and beverage, pulp and paper, textile industries, and then we can see the level of heat temperature required that could be covered by the geosyn solution. So I want to try to draw my conclusions, and particularly geosyn tries to demonstrate the viability of medium-grade geothermal heat in order to provide both heating and cooling for industry. The innovative part is the utilization of R718 water as working fluid, both for the high temperature heat pump and for the cooling cycle, which are totally heat-driven, and both technology are showing potential for the coupling with the industrial sector and are especially effective where the concurrent heating and cooling are present. So paving the way to an energy efficient and decarbonized manufacturing. Thank you very much for your attention.
Thank you very much, Lorenzo, for the very attractive presentation. I'm reminding to our audience about putting their questions in the chat in order to have the very productive Q&A session in the end. Meanwhile, I'm happy to present the next speaker, Anso Pardinas from Geos Technis project, who is representing ITG Technology Center. The floor is yours, please.
Oh, good morning. You can hear me. You can see my slides as far as I can see. So thank you very much for the introduction, Taras. And yes, so my name is Sancho Pardinas. I represent ITG in Galicia, Spain. And I'm also scientific coordinator for Geos Techis, which is a sister project to geosyn, which was already presented by Lorenzo before. And actually, his presentation will help me a lot to introduce our topic in a way. So my point today is to introduce Geos Techis project. And for that, let me give you some context. So it was already mentioned, but still we know that industries, according to the International Energy Agency, industries take around 30% of the final energy demand worldwide. And from this, 2/3 approximately are in the form of process heat. Process heat, typically covered by fossil fuels and other, with the environmental impact these technologies have. Yes, from this 20%, around 50% is in the range of 200 degrees Celsius or below. And as already discussed today, high temperature heat pumps appear and are developing as a very, let's say, promising technology to meet these thermal demands at these temperatures below 200 degrees Celsius. There are already systems in the market, and it's a very much developing technology these days. However, to make these heat pumps for industrial processes as efficient as possible, we need a reliable heat source, or a heat source reliable but also at sufficient temperature. And geothermal resources in the range of, let's say, 100 degrees Celsius could make a good opportunity to this, and they could be in a way located in more widespread than the conventional uses of geothermal energy for electricity production nowadays. And this is in a way the context that powers GeoSteckis. So GeoSteckis is a EU-funded project with the focus of decarbonizing industrial thermal processes with geothermal energy and other technologies that have been or are being developed around geothermal energy. And we are 10 partners plus one affiliated, spread all around Europe and working collaboratively in this project. So basically, the general picture is not very different from Geosyn in a way that we are building in this binomial of geothermal energy at the low, medium temperature range, so around 100 degrees Celsius or so. And we are developing technologies to meet heating and cooling for industries, for industrial demands. Of course, to bridge this gap, there has to be some thermal system that we will introduce later, and some other technologies which allow us to take the most out of this binomial of energy, geothermal energy, and the demands we are trying to meet. All in all, in GeoSteckis, we are trying to support green transition of industrial thermal energy, reduce the carbon footprint of these industries, contributing to the EU Green Deal, and developing technologies which are transferable to other sectors, not only to the demo site we will introduce later, but also to different heat sources, which could be, in a way, working together with geothermal or even substituting geothermal totally. So please let me now introduce the 5, let's say, objectives and specific objectives and innovations within GeoSteckis, which in a way we will develop, or we will delve into them later in some other presentations, but I will try to introduce them today to the audience. So first of all, we have what we call the GeoSteckis thermal system. The GeoSteckis thermal system is in a way the solution, the technology that will allow us to bridge the gap between the geothermal heat source we are aiming, those 100 degrees Celsius, and the process heating at around 200 degrees Celsius and cooling above 0 degrees Celsius we want to meet. For this, we have a specific presentation today in session 2, which will be given by my colleague Christoph Vanasiak from Sintef Energy. I really hope you will be present there, and he will introduce a little bit further the technology. But the idea is that we will have a system which integrates 2 solutions based on natural refrigerants: a water R718 high temperature heat pump plus a propane ejector cycle, utilizing the low grade heat to produce cooling. The second of the objectives and innovations within GeoSteckis is to push the limits that currently exist for thermal energy systems, storage systems, and underground thermal energy storage in a way that we can push them further in temperature. Currently, they are basically limited to 90 degrees Celsius or so, according to the literature. We want to help, or to bring, let's say, that our contribution to make them more suitable for industrial flexibility. We are trying to identify the right concepts and model them so that these thermal energy storage systems become usable not only for our, let's say, thermal system, for the high temperature heat pump plus ejector system, but also for direct use in industry. All in all, thermal energy storage will contribute to the stability of the industrial process and also let us leverage heat sources such as maybe industrial waste heat or solar energy or other renewables. And a very important part of this, let's say, work we are doing in Geostekis is to develop innovative heat transfer fluids, namely nanofluids, which allow us to store energy at temperatures which water or non-pressurized water does not allow us. So we are developing these fluids which will allow us to store energy at 100 degrees Celsius or above with excellent heat transfer and heat storage capabilities, and of course, non-toxic and safe to use. It's very interesting, I mean, to have the right technologies in place, but of course, there's also important to manage them in a right way. And to do so, we are working in a specific work package on supporting the decarbonization of industrial heating and cooling through digitalization and digital tools and technologies. And we are doing it in two different ways, or let's say in two branches. One of them is to optimize energy management. And we optimize energy management with the development of an industrial Internet of Things platform coupled with hybrid digital twins, which in a way allows us to visualize, store, and operate according to the data we are retrieving from the industry. So we are retrieving those data, we are able to make predictions and forecasts of how the system should work in order to make the optimal use of energy we have available in our system. And the other line we are working in is to make this, let's say, the knowledge we are getting from the project, make it usable for other industries, providing what we call the decarbonization potential evaluation tool. So in principle, any industrial user could bring us their data, and we encourage you to do it actually, to bring data on their demands, temperature profiles, when this happens, where they are located, which are the current systems they currently have, so that we can use this data in our decarbonization potential evaluation tool and provide what we call decarbonization roadmaps or decarbonization strategies. So we will provide, let's say, different levels of CAPEX investments that could provide decarbonization to those industries, and providing the right metrics, the techno-economic analysis and the environmental impacts and indicators, those, let's say, those roadmaps will have in the industry. The fourth of the objectives and innovations within Geostekis we're working on is to support decision-making of the geothermal heat potential of a specific location. So as you know, currently exploration costs for geothermal energy are quite big, are quite large. There is an uncertainty when you explore for a geothermal location in particular, and there is a risk associated with it. And we are working with our colleagues from A-Town on what we call the IAGEM, the A-driven geothermal resource mapping. So it's in a way a technology which, or a tool which based on data which is available today, so satellite data, geophysics data of a certain location, will be able to bring us the right outputs on whether a specific location can be suitable or not for the geothermal use, and at which temperatures and at which, let's say, depth, etc., etc. And last but not least, the fifth of our, let's say, objectives. So there is a lot of, let's say, misconceptions around geothermal energy, geothermal supported energy systems, and Geostekis is trying to promote the knowledge and acceptability of these systems. First thing, by assessing properly the environmental and societal impacts they actually have. And we have in session 2 today a presentation which will be held by our colleagues in Leitat, in Catalonia, Spain, around this topic. So I will not disclose too much right now, but the idea is to be able to actually assess what is happening in this kind of systems, to understand also which is the actual knowledge of society and industry on the potential of these systems. And in the end, we will provide in GeoSteckys materials to communicate our findings and educate, if we can say it like this, industry or stakeholders around the topic. And last, I would like to introduce, let's say, the company, which is our partner and company, which is everything possible in the end. It's helping us or allowing us to validate all these technologies and developments, which is Kauman, which is a, let's say, partner of our project, and they manufacture conveyor belts, power transmission belts. They are located in Galicia, in Spain, northwest of Spain, above Portugal. And it's the perfect example of industry combining heating and cooling demands at the temperature levels we are aiming here at GeoSteckys. So that has been all for me. Please do not hesitate to write your questions or ask them later today. And yeah, I'm open to any feedback. Thank you very much.
Thank you, Anso, for your presentation. It was indeed very, very informative and great. And yeah, let's move to our next speaker, Michael Bayer, a research associate from the CERN University of Applied Science and Arts, and also from Institute of Building Technology and Energy from Switzerland. And he will represent the case study from Interstores project. Michael, the floor is yours.
Thank you very much for introduction. I don't know if you can see my screen.
Yes, we do.
Okay, perfect. I will start. So today I'm going to talk about the development of a reduced order model for seasonal thermal energy storages, which is part of the Interstores project. If you're interested in the project itself, you can scan this QR code. It will direct you to the homepage. And I will show you some results of our recently published paper. If you're interested in the paper, you can find the link here. So what is the motivation behind this? This is part of Interstores, and Interstores itself brings together 14 partners in 9 different countries, and it focuses on optimizing and implementing seasonal thermal energy storage at 2 demo sites. One demo site is the Incampus in Ingolstadt. It's a gravel pit, and the Varanto cavern storage in Finland with a size of like 1 million cubic meters, which would be the biggest cavern storage so far. And one aspect of us from HSLU was the development of a reduced order model in Modelica, which is both fast and accurate, so it can be then used for system simulations in real environment. So the issue so far was that we don't have measurement data yet, so we had to come up with a process how to create this ROM. Therefore, we used a validated COMSOL model created by AIT, which is one of the project partners. And the issue with this one is that it's rather detailed and quite computationally intensive, and therefore it's impractical for the real-time system simulation. And to address this, we created the reduced order model in Modelica. So how did we proceed? We defined similar input parameters and boundary conditions, which were then fed into the COMSOL multiphysics model, which then created results. Parallel, we created the reduced order model in Modelica and then did the calibration process in order to match the results from COMSOL and have something fast, which is suitable for like digital twinning. Here you can see the key design parameters which we used. So the parameters has like different size variation. We made simulations from 20,000 up to 200,000 cubic meters with the given parameter here in the list for like soil and fluid and so on. The simulation itself, we made 5 complete annual cycles, where one cycle is represented by 90 days of charging, 90 days of storing, 90 days of discharging, and 90 days of idle phase. In total, we make 5-year simulation, and for comparison of the results, we use the 5th year. Here you can get a quick insight on the COMSOL model which was used. It's the De Plates model developed by AIT. and this is supported by the finite element method, and it includes multiple features. So you can simulate all kinds of different S-test systems with it. And for this study, we focus on a water-based system without groundwater flow in the soil. This is the reduced order model we created within Modelica. It mainly consists out of 3 components. One is like the stratified tank model, the second one is the buoyancy model, and the third one is the ground model. Both the stratified tank and the buoyancy model were based on the buildings library, and we made strong modifications. So in order to first represent the proper shapes, in our case for this study the truncated pyramid, but the model itself can represent from cone to pyramids to cylinder, basically all kinds of shape. We used for this equidistant discretization. For the study, we used 200 layers within the tanks, and you're able to connect basically each layer of the tank with in and out flow connections. Then for the ground model, we created a 2D grid with finite volume method, where each element represented by a 4R1C network to simulate the interactions between the ground and the tank. Here you can see results we got from this study. The thermal losses from the tank itself, particularly for the uninsulated variations, are shown here. We also did simulations for the insulated, but the difference are marginal in this case. So as you can see in this chart, the side losses play a dominant role, especially as the size decreases. For large tanks, the side losses are roughly 50% of the total losses, and for smaller tanks those increase to up to 66% due to the higher surface volume ratio. Bottom losses in total are the smallest contribution, overall sizes ranging between somewhere 7 and 9% of the total losses. Even though we have slight disagreements, the overall alignment between the Modelica model and the COMSOL results stay in an acceptable range, somewhere between 1% and minus 2.5%. Here you can see the temperature profiles for the different S-test size from 20,000 to 200,000, representing 5 relative heights within the storage. So where 95 is the layer close to the lid, and the 5% represents close to the bottom of the storage. So you can see quite close alignment, especially during the constant conditions, but as soon as dynamic events occur, the temperature profiles from the 2 models show minor deviations. For example, during charging, the Modelica model initially underestimates the temperature slightly, but once it continues, it slightly overestimates by 1 Kelvin. Those differences are largely due to solver settings and the different discretization methods used. So the COMSOL model uses like advanced solvers and integrating the energy balance equation over the entire discretization element, but Daimler, for example, exports the temperature data at the center of each cell corresponding to a relative height and follows a nodal approach. Here you can see the root mean square error distribution of the 5 chosen layers. The deviation between COMSOL and Modelica were on average somewhere between 1.2 and 2.4 Kelvin across the different layers, and this level of accuracy basically underscores the robustness of our model. Although there is still slight room for improvement, for example, in extreme cases when the tank is very small or rather very big. What's also to mention here, as you can see, best performer is the 100,000 cubic storage, but this is based because we started with this one and all the calibration and validation was done with this, and then we scaled it up and scaled it down. If we take a look at the energy balance, you can see that the Modelica model consistently underestimates both the charged and the discharge energy compared to COMSOL by roughly 5%, but this is also mainly due to temperature evaluation inside the tank. So smaller storages basically have higher surface to volume ratio, and in these cases, the thermal losses are more dominant and the stratification is less important. But for larger systems, they have stronger thermal gradients and more strong stratification, especially near the inlets and the tank bottom. So the COMSOL model itself captures those behaviors by using a fine mesh and a fully coupled physics. But the reduced order model employs a simplified layer-based structure and buoyancy treatment. So as a result, small temperature mismatches can accumulate into more noticeable deviations as if the simulation time is longer. For the computational time, you can see the comparison between Daimler and COMSOL. So we optimized the reduced order model by calibrating the segment count based on convergence tests to ensure a stable stratification without excessive runtime. So in COMSOL multiphysics, there is a direct fully coupled approach with the adaptive mesh refinement and by use of the MML solver. And in Daimler, we used the Dussel solver, and we ranged time steps between 10 minutes and 1 day. For both comparison, we used the same machine, and we were able to reduce the simulation time by up to 98%. Which already brings me to the conclusion. So the reduced order model has demonstrated strong performance, achieving deviations of less than 2% in temperature simulation. And during the calibration against COMSOL simulation, the model was, let's say, highly efficient, and we were able to complete a full year simulation in roughly 4 seconds. I mean, for example, if we simulate something like Dronninglund, which is highly complex, then it increases. But for example, annual simulation for Dronninglund, we still manage with roughly 1 minute simulation time. What are we now planning to do? So first of all, we already did the FMU export, and we are about to perform some parameter calibration with FMPy. And then additionally, we will working on different storage media, for example, the gravel water mix. And then, which is also ongoing, is like model refactoring, so we can make it accessible to other person and more usable. Ultimate goal at the end is then to implement this one in an MPC and then install it on one or both of the demo sites once they start operating. Thank you very much.
Thank you very much, Michael, for the insightful presentation. And let's move to the next speaker, Andrea Frazica from CNR, who will represent the REWICH project with the topic Heat to Cold Industrial Solution. And yeah, Andrea, the floor is yours.
Good morning, everyone. Hope you can see my screen.
Yes.
So, thank you for the introduction. My name is Andrea Frazzi. I'm the coordinator of the REWICH project. Actually, as you will see, REWICH is probably the first one among the projects that are presented today that is not dealing with geothermal technologies, but mostly focusing on the heating and cooling solution for industrial applications. So the presentation will be mostly focused on an overview of the project itself. REWICH was started almost 2 years ago in January 2024 with 26 partners from 10 countries and yeah, roughly 10 million euros budget, at least from European Commission. As you can see, we are spread more or less all over Europe, trying to focus on the development of different technologies to be validated in 4 different industrial demo sites. So I'm focusing here a bit more on the, let's say, specific summary of the project. As mentioned, REWICH is focusing mostly on providing innovative cooling solutions for industrial applications. Of course, as you know, in general, industrial processes are mostly considered energy intensive from the heating demand point of view. Nonetheless, there is still a huge requirement for cooling provision also in industrial processes. For this reason, we are targeting the development of different technologies that can be easily integrated inside industrial processes, but not using, or let's say using only partially electricity to drive their working cycle, while mainly exploiting thermal energy as a main driver. So the idea is to have basically two different heat sources to drive our cooling technologies, either low-grade waste heat recovered by the industrial process itself, or solar thermal installed in the process. Our idea is not to provide purely solar cooling solution, because it turned out already in previous project that this is technically feasible but not economically viable. So our idea is to make the process as economically feasible as possible, which means that we are trying to find the best techno-economic integration between the waste heat availability and the solar thermal collector installation. So this heating is then used to drive sorption processes. I will show you a bit more in details which technology we are trying to develop in the project. So we have 3 different technologies that are working in parallel in this development phase that will be able to provide cooling to different industrial applications. More specifically, we'll have 4 demo sites that are covering different industrial processes, from the, let's say, the most standard ones that are usually food and beverage, up to innovative industrial processes, at least from the cooling point of view, which are biorefineries and pulp and paper sector. And we'll also further replicate this investigation through modeled demo sites in 3 different replication sites. So, as mentioned, the core of the project is the development of innovative sorption processes for cooling applications. In particular, we have 3 different technologies that are currently under development. The first one is an innovative adsorption technology. Adsorption means that the sorption process is happening thanks to the use of solid sorbent media, in this case silica gel. But the main innovation in this technology is related to the patented solution that is proposed by the German company Sorption Technologies, in which they try to reduce the number of components of the technology itself by having the adsorbent reactor integrated already with some evaporator and condenser inside the reactor itself, so minimizing the number of heat exchanger inside the process, so exploiting a direct evaporation and condensation inside the reactor. And this solution is also conceived as stackable as possible. So in a modular way, you can see here, for example, a system consisting of 3 modules working in parallel. So you can, in principle, increase the capacity, the cooling capacity that you want to install by stacking more modules together. The other 2 technologies are belonging to the absorption one. So in this case, from the physical process, the main difference is that the adsorbent material is a liquid solution. In our case, for both technologies, we are using lithium bromide solution as an absorber. Here we are evolving an already existing technology, which is provided by the company BS Nova, which is a kind standard lithium bromide water absorption chiller, by adding 2 new features. The first one is the integration of a water vapor compressor inside the cycle, so creating an hybrid absorption chiller. This will, from one side, improve the flexibility in operation, because we can maximize the exploitation of local waste heat, but also renewable power on site to drive the compressor and maximizing the operation of the chiller also in extremely harsh environment, for example, when the ambient temperature for recooling is very high. And the second feature is that we can also co-generate heating, because we can exploit the hot sides of the condenser to preheat process inside the industrial plant. The second technology is, on the contrary, working on the evaporator side. So in this case, we are developing a technology that will be able to provide at the same time 2 different temperature level on the cooling side. So to satisfy 2 different cooling needs inside the industrial process. So all these technologies are now in the phase of manufacturing. So we have completed their design and preliminary testing of some components. The next phase will be the manufacturing and testing under controlled conditions in the lab. The other technology that is, of course, needed for the full system is the solar thermal collector one. In this case, we are not going to develop a new technology, but profiting of existing one provided by the Swiss company TVP Solar. This is a kind of unique technology because they are working with the flat plate solar collectors, but fully operating under vacuum, which means that they minimize the heat losses, so they can reach up to 200 degrees C even without concentrating solar technologies. This has a very good, let's say, selling point because the installation in the plant is much easier. You don't need any concentrating, any tracking, and in the end, also the maintenance is much easier. So in this case, our target will be to install this technology in parallel to the existing waste heat in order to provide heating to our sorption cycles. And the other point is on, let's say, the designing of the demo site. So we are basically working with 2 parallel tracks. One is profiting of a digital twinning environment to maximize the efficiency in the design. We are now in the phase of collecting all the information of the existing demo sites, creating digital twinning for all the demo sites, and then implementing them with innovative ReWitch solutions in order to make the designing phase as smooth as possible, and then also profiting of BIM modeling to make the overall demonstration campaign as interactive as possible with an historical, for example, possibility to check all the installed equipment, but also with a live dashboard that allows us to track the operation of the system online. And at the same time, we are developing simulation studies that are helping the sizing of all the components inside the plant. Here, just an overview of the 4 demo sites. As mentioned, we have 2 demo sites that are belonging to standard, let's say, plants for cooling demand in industrial processes, which is a brewery in Poland and, let's say, a dairy plant in Spain, Covap. And then we have 2 other plants that are belonging to, let's say, industrial processes that are usually not so considered in cooling processes. Basically, a biomass and biofuel refinery in Greece, the Mill Oil one, and a pulp and paper company in Italy from ICP. Here, just quickly, an overview of the current status of the different digital twinning that we are developing for the 4 demo site. Of course, we are now working on the current configuration, so we are trying to model all the section of the plants that are interested by the ReWitch integration. Next steps will be to profit of this preliminary digital twinning to derive the designing phase of each demo site. So what's next? As mentioned, we are now in the manufacturing phase of the first prototypes. This will be ready probably by the end of this year, and then early 2026, we will start the testing campaign in the lab infrastructures that are part of the project, in order to finalize the design, also to optimize the operation of the technologies. We are now working on the cloud-based monitoring system that will be installed in all the demo sites to start the data collection for the baseline analysis that will last for the entire 2026. And then, as mentioned, we are finalizing the design of the demo sites. We expect to have the design finalized by the first months of 2026 to move on with the procurement and the installation of the equipment in all the demo sites until the end of 2026, in order to be ready to receive all the technologies on site and install them to start the final year of the project that will be mostly dedicated to the monitoring of the technologies operation. Here is an overview of the consortium, and thank you very much for your attention. Of course, I'm very happy to answer any question.
Thank you very much, Andrea. It was indeed very insightful. Meanwhile, let's keep our timing and let's move to the next speaker. The next speaker is Simon Müller from the project Interstores, with the presentation topic implementation of the expanding thermal source network as a step towards CO2 neutral industry. Simon, the floor is yours, please.
Thanks a lot. So yeah, thanks for the introduction. So yes, my name is Simon and I'm a researcher working at the University of Applied Sciences in Ingolstadt, Germany. And I'm happy that you decided to join today and listen to my presentation about a modern benchmark of an adaptive thermal source network. And we will see what that means in a second, at an industrial site called the InCampus, which was already mentioned earlier by Michael Bayer. The research related to this presentation is part of the Interstores project. As introduction, we will have a short look at thermal source networks in general. Afterwards, we will already dive into the specifics with a system description, and I also brought some examples about the envisaged operation, first monitoring results, and one exemplary planning step. Some of you might already know the concept of thermal source networks, short TSN, and the IEA-DHC Executive Committee defined them as networks that are mainly used as a source for heating and cooling by decentralized technologies such as heat pumps. A picture of that you can see on the right side. And there are multiple benefits of these systems, but I would only like to mention two right now, which are the low temperature levels of these grids, which makes integration of renewables easy, and the heating and cooling can be facilitated with the same infrastructure, which increases energy efficiency, and we will have a closer look of how that is achieved later. But with those two aspects of TSN, you can already see that they can help to move to a more climate-friendly future. And today we're going to take a look at the system, which can be seen in some parts as a modern benchmark of those TSNs in terms of retrofitting industrial areas, in terms of multi-source and multi-storage integration, and in terms of modularity and adaptability. The TSN I'm referring to is called the InCampus, and the InCampus is a planned 75-hectare industrial park, which will consist of up to 70 non-residential buildings. And the area of this project is situated in Ingolstadt, Germany. But before I show you some recent information about the InCampus and the related energy system, I want to have a quick look back in time and see what was happening at the InCampus before. Until 2008, the area we're talking about was occupied by a refinery, which started operation back in 1965, and sometime after the refinery shut down. The area was sold for €1 symbolic to the city of Ingolstadt and Audi, which is also located with its headquarters in Ingolstadt. Both partners agreed to plan to refurbish the area into an open technology park, and now we can already see that path from the old refinery site towards this new TSN system called the InCampus. And all of that process started with a soil remediation process to get rid of all the contamination that was left from the operation of the refinery. And 90% of the washed soil was again used on site, for example, for land leveling. And some of the gravel part that was washed will or is right now be used or utilized in the combination with old fire extinguishing basins, which you can see here, to build a seasonal thermal energy storage, which Michi Bayer mentioned earlier, which is part of the Interstores project, which is pretty cool. So we're using pre-existing infrastructure to build seasonal thermal energy storages. Next to that, there are also groundwater wells, which keep the remaining contaminants from being washed away, and those can also be used as a thermal source or sink for the TSN, which you will also see later on. And now that we're all cleaned up, we can start with the current state. Currently, the in-campus is still under development. Overall, there are 4 construction phases planned to develop the whole area, but since September 2023, the first 4 buildings of the construction phase 1, which you can see here, went into operation and were connected to the TSN. The TSN infrastructure itself, on the other hand, is already installed, so pipes, or equipped for the following construction phases. It just needs new buildings to connect to it. And now we will have a closer look to the envisaged operation of the buildings and networks in construction phase 1. There are 12 buildings planned for construction phase 1, some office buildings, a security center where security features of cars are tested, and a data center, which has a significant waste heat potential. The demands of all those buildings in construction phase 1 sum up to around 7 gigawatt hours of heat demand per year and around 26 gigawatt hours of cooling demand. And what you see on the bottom of the slide are the projected load profiles. In blue, you can see the cooling loads with an offset because of the steady, more or less steady cooling needs of the data center, and in red, the heating demands. And you can see that a lot of the time those demands are overlapping, starting in September all the way through winter until mid of May. There is something which can be called balanced demand. This is the case when one of the buildings connected to the network has a heating demand and another building, because of its function or utilization, has a cooling demand at the same time. So in end of October, for example, the data center with its cooling demand will eject heat into the network via heat exchanger. And on the other end of the network, some office buildings with heating demands will extract some heat via the heat pumps. So instead of fulfilling the demands separately, the demands are balanced in the TSN. The primary energy demand is reduced and energy efficiency increases. For the first construction phase, it was projected that more than 10 gigawatt hours of thermal energy demand can be balanced throughout 1 year. For every demand that cannot be balanced, there is need for additional sources and sinks, which we can see here. We see the Danube River, we see additional recooling plants, and more to the south of the area, we see the groundwater wells, as mentioned before, all of which offer thermal power for heating and or cooling. Equally important or central to the energy system are the storage capacities. Here we see the firefighting water tanks in the energy hub, which are used as a buffer storage, and we have the network and surrounding soil as an inertia, and then the seasonal thermal energy storage, which is currently under construction but in the final stages of construction. And now we bring all of these components together, and we can understand the envisaged operation. In the center, there's the TSN, which is connecting all the different components of the energy system. Now, during winter, the buildings have a dominating heating demand, which is to some extent balanced by the waste heat from the data center. Additional heat supply can come from the thermal sources or discharging the S-TES. Now, during summer, the demands of the buildings change, and most of them will have a cooling demand, or you could also say they supply exhaust heat to the network. The waste heat from the data center does not really help with that, but adds even more heat to the network. Accordingly, all the surplus heat is either charged into the S-TES, which is just another way of saying there is cold discharge from the S-TES, or the surplus heat is discharged to the displayed heat sinks. That means, for example, groundwater wells or Danube are providing cooling energy, and that is why the blue arrow is directed towards the system. Yeah, before I mentioned that 4 buildings of the construction phase 1 went into operation 2 years ago now, and for those I can present some monitoring results starting in July 2023. You can see the summed up cooling demand of the buildings in dark blue. Right next to that, you can also see the cooling energy supplied by the groundwater wells in light blue. And you might recognize that the light blue bar of the supply is a little higher than the dark blue bar of the demand. This is because there are some cooling losses to the ground in these months. In May, you can see a more extreme behavior, exactly, which is related to the temperature level of the network and the ground. Starting from October onwards, you can also see the summed up heating demands of the buildings in dark red, and next to that in light red, the heat which was supplied by the waste heat of the data center. And although the network temperature of the TSN is kept around 15 degrees Celsius in winter, there are still some heat losses to the surrounding ground. But as you can see, groundwater and waste heat can supply necessary thermal energy for the current system. And that is as far as I would like to go about the monitoring today. Yeah, but I brought some more insights into the technical project planning of the in-campus for reviewing the overall documentation of the project. The 5 main phases of the technical project development on the left were derived, and because I do not have the time to go in all to the chapters in detail, I brought one exemplary planning step, which is the comparison of different network types. There, the planning committee had a look at 1, 2, or 3 pipe systems and compared them to each other in different categories, more than are shown here. One of the highly weighted categories was energy efficiency, and it was correctly identified that a unidirectional 2-pipe system has some shortcomings compared to a bidirectional 2-pipe system in this regard. But from the point of view of the planning committee, the point was outweighed by the complexity of the control and complexity of the installation of the system itself. So therefore, it was decided to operate this system as a unidirectional 2-pipe system. Yeah, now we've seen a brief overview of the in-campus energy system, and in some details we were able to grasp maybe the benchmark properties of it. Originating from a former refinery site, the in-campus presented itself as a benchmark in terms of retrofitting. With the planned operation, we could see the multiple sources and multiple storages that are already included or will be included. And from the first monitoring results, we saw the system's operation in partial load now, but even more important that the energy system planning that considers the modular expansion and the integration of many more industrial demands in the future. And accordingly, future research will be oriented at maybe transferability of the system. And the first step in this regard is to analyze the planning process, which we did. So we have more steps ahead. Establish the energy monitoring to have a continuous report, not just once, and also go more in the direction of control systems, including the seasonal thermal energy storage, and maybe starting to have a MPC at the in-campus. Yeah, that would be all from my side. So thanks for listening, and I'm happy to answer questions in the chat or later in our Q&A session.
Thank you very much, Mikhail, for the presentation itself. And we are a little bit tight in our schedule, as I mentioned before. Meanwhile, I'm still have invited the audience to put the questions in the chat. And I'm happy to present the next speaker, Hemendra Sharnagat from the project Hook Loop. And the topic is a closed loop deep geothermal solution. Hemendra, the floor is yours, please.
Yes. Can you see my presentation?
Yes, we do.
Yes. Hi, my name is Hemendra Sharnagat, and I'm representing Geotherma and also presenting in behalf of my colleague Ola Vastavik. So the Hope Loop project is based on around 10 partners with this project and coordinating with Institute for Energy Technology, IFE, from Norway. And we are the Geotherma, the railway subsidiary company from Norway. And you can see all the partners named here. The main objective of this horizontal closed loop for deep geothermal heat extraction. So, we are finding the new solution to allow heat extraction from any potential location where we can use, develop and demonstrate the technology, plus develop and validate the computer model, which is mostly done this part by IFE, and also investigating the potential EU pilot sites, also investigating alternative circulation fluid so it can improve the electricity production and performance. And also with that, we are assessing the environmental aspect and social acceptance for implementation. So these are the objective of this HOC loop project. In this slide, you can see here, we have the open loop conventional 2 wells, where you can see we are using the single well. We called it closed loop. So that's what make it very different from the conventional open loop wells. So the next slide you can see here also, this is the graph generated based on the computer model and prepared by IFE. So in the long term, you can see at least in the graph, it says like time span of 40 years, but once it stable the level, so it can maybe go for forever, I can say, or at least 100 years. That's what we are looking at this solution. And this closed loop project or this the technology we have used dual vacuum insulated tubes. So the very important aspect of this project, the technology we are using, the dual vac. So this is the vacuum chamber or annulus, we can say. So which can protect or minimizing the heat loss. And that's what you can see in my right hand side. These are the tubes we have used for this project. So it can minimal the thermal loss on fluid. Yeah. And it's continuous, vacuuming along the whole tubing in the well. In the next slide, you can see we have tested the full scale test in Ulrich Test Center in Stavanger. So approximate around 650 meter dual pipe we have used to perform this pilot test. Also, it verified the heat flow model by thermal response test. Next slide, you can see also the picture from the site. You can see all the laying down all the 12 vac pipe. We also called it DHS, dual heat string. So that's what we given the name of these pipes. And some more picture from the original from the site. Yeah. So here is the conclusion. The model for heat flow, it's been verified, and also we are improving the heat flow model, and IFE it's working on that. Also we have done this full scale test at Ulrich, and also currently evaluating the potential sites. And further work, like we want to use also like alternative fluids options, so which can improve the performance, and also it can increase the power by new well construction. And as I already mentioned, this portability, this solution can be used in any location where are the potentials. So it's very short presentation, and thank you for listening. Yeah.
Thank you, Hemendra. Yeah, thank you very much again. And yeah.
The questions can be addressed to the Ola actually. So I'm just holding this presentation. Yeah.
Yeah, thank you very much. Yeah, for the audience, please keep the question via the chat, and we will come back with that in the end. Actually, I just wanted to remind that for the time being, we are planning the last but not least the presentation before Q&A session for the first thematic session, and after that we will have a short 10 minutes break. So the final presentation on this thematical session will be provided by Connie Okando from Your Heat and Power. She's PhD project officer, and she represents the project Uses for Heat with the topic Decarbonization Heat, how seasonal storage can power the clean energy transition. Connie, the floor is yours, please.
Thank you very much. You can see my presentation, right?
Yes.
Okay, good morning, everyone. I'm Connie Okando, project officer at Your Heat and Power. And today I will be sharing insights from the Uses for Heat project. We will explore how seasonal thermal energy storage, in particular underground thermal energy storage, can help decarbonize heating and support the clean energy transition. Okay. So here is what we will cover today. First, we will talk about the heating challenge, the role of underground thermal energy storage in heating, the technology that we are developing under the Usage for Heat project, and the impact we expect from this project. Heating and cooling account for around 50% of the Europe's energy demand, and around 74% of this still come from fossil fuels. So this highlight the urgency for the need for clean energy alternative. As we can see in this table, that the share of renewables in the Europe heating sector have increased over the past 2 decades at an average of a rate of around 0.8 percentage per year. However, there is this increase. We need to meet the 2050 climate target. We need to significantly accelerate the deployment of renewable energy. So to achieve a 100% share of renewable for heating and cooling is essential. This is essential for a truly clean energy transition. So but this is not only a climate issue, the heat decarbonization, it's also a matter of energy security. So we must make the Union independent from Russian fossil fuels by 2030. And there is where district heating comes in. District heating is a centralized system that distributes heat to multiple buildings. So it is a key technology for decarbonizing our heat systems. And why? Because district heating allows for multiple renewable inputs and also allows the integration of energy storage and, of course, improve the system resilience. As we can see in this table, by 2050, district heating is expected to supply heat to over 250 million people, and with a market share growing from 13% to 48% by 2015. So achieving this growth will require, of course, a major infrastructure expansion across Europe. So why underground thermal energy storage integration? So as we can see in this diagram in the left side, a district heating system can be broken down into 4 different parts. That is the production of heat or cold from an energy source, the distribution and transmission piping network from the source or the plant to the end consumption, But before the end consumption, we can have a storage, so thermal energy storage. That is a technology that stores heat or cold for later use. For example, capturing excess heat in summer to use it during winter. So this technology helps district heating system operate more efficiently and enables better integration of renewable energy sources by balancing the mismatch between energy supply and demand. Here in this diagram, we can see the different types of thermal energy storage technology, and we are going to focus today in borehole thermal energy storage and aquifer thermal energy storage, that are the technologies being developed in the Used for Heat project. So what is borehole thermal energy storage? This technology stores heat in underground rock or soil. Uses vertical boreholes with U-tube heat exchangers carrying heat transfer fluid. The efficiency of this technology depends on the borehole design, the pipe material, and the thermal conductivity. This technology shows easy scalability and limited geological requirements that make this technology highly appropriate for large-scale installation. Then we have aquifer thermal energy storage. This technology stores heat in groundwater within porous aquifers, and the heat is accessed via drill wells into the aquifer. This technology is restricted to a few locations due to the geological condition and limited drilling capabilities. So here, Uses for Heat is demonstrating 5 key technologies to enable cost-efficient, optimized seasonal storage heating. And these are first, we are developing advanced aquifer thermal energy storage drilling equipment with remotely controlled machines. We are also developing innovative high-temperature groundwater heat pumps connected to aquifer thermal energy storage and, of course, to district heating networks. We are also developing highly efficient and cost-effective solar thermal collectors. Of course, this will be integrated with high-temperature boreholes. Thermal storage, and also innovative larger piping for high temperature boreholes. And we are also developing enhanced solar hybrid PVT panels. We have assessed the viability of these 5 technology at 2 demo sites in Italy and Norway. In Italy, the demo site is the Riva del Garda. We have developed the drilling unit manufacturing. It's nearly complete. And also the PVT absorbers were tested and the groundwater heat points component were defined. Nevertheless, we encountered some issues because the lack of regulatory frameworks in Italy and, of course, the limited geological knowledge. In the demo site of Førset in Oslo, Norway, we have tested successfully the pipes and the solar thermal collector integration. And in this case, we encountered some issues because of the investment portfolio shift of the company. Due to this, we have to implement some mitigation measurements, and the 2 demo sites, we have identified 2 new demo sites because the previous demo sites in Riva del Garda and Førset will no longer continue in the project. But this, in this case, we already have some mitigation measurements. As I said, we have 2 new demo sites that offer comparable operational, geological, hydrological, and energetic conditions, and we are pending the approval from the European Commission, and we expect a positive decision by the end of the year. So I wanted to highlight this to show you the barriers that these new technologies can confront during the development of these kind of projects. So, but the 2 demo sites, new 2 demo sites are underway. So with promising results because we are already address some challenges in the study of the feasibility of the previous 2 demo sites. So in conclusion, what we expect from the usage for heat is to increase the availability, robustness, and safety of sustainable and efficient choices for energy storage, to increase security of supply, reduce energy loss, cost effectiveness, and improve the environmental footprints of the energy system. We expect to increase the technology leadership, competitiveness, and technology support potential of European storage technology industry. We expect to enhance sustainability of storage technology, taking fully into account circular economy, social, economic, and environmental aspect in line with the European Green Deal priorities. And also, usage for heat will not only demonstrate to underground thermal energy storage, but also different technologies like solar thermal collectors, water heat pump, which will enable the exploitation of different heat sources like solar thermal energy, geothermal energy, industrial waste heat, and hybrid solar panels. So these heat sources will be fully integrated and connected to the thermal energy storage units, demonstrating the sustainability of this technology to accumulate various heat streams. That's further maximizing the flexibility of the sector and its decarbonization. So thank you very much, and this is all from my side.
Many thanks, Konya, for the presentation. So, as I mentioned before, this is the last presentation within our first thematical session, and we now are planning to have the Q&A session afterwards. So I'm happy to ask the first question we've achieved from our audience. So Marriott Bilius asking Simon Mueller about the temperature thresholds of the thermal stainless steel pipes they are using within the project. Simon, please, if you are able to answer.
Yes, so I answered this in the Q&A section, but I guess I can also do it audio-wise. So we have some strict limits for the operation. So temperature should not drop below 5 degrees Celsius, because then we have some freezing maybe in some regions of the network. But other than that, we're not limited to a lower limit. And 45 degrees Celsius is the upper limit, because actually the pipes are plastic pipes and they are uninsulated. And so material-wise, if we have for long periods higher temperatures, this would be bad for the material. And in between, it's just a matter of optimization. Do you want to accept more losses in the distribution of your thermal energy, so whether it's heating or cooling, or do you want to have better efficiencies with the decentralized heat pump? So do you want to have high supply temperatures for every heating demand, and then higher heat losses, or the other way around? And I mentioned this also in my answer. At the in-campus currently, the temperature in winter is around 15 degrees Celsius in the central network, and in summer it increases because of all the waste heat that's discharged into the TSN, and then you have high temperatures in the network and it's uninsulated, so you have some cooling gains from the ground, so that's the benefit there. But there's for sure many more operation scenarios that we could try, and we're planning to do that with the MPC to find an optimum. Yeah, but that could be, so in Ingolstadt in Germany, there's one optimum, and if you have a different system, so same technology but different prices for heating and cooling and electricity, your optimum would be somewhere else.
Okay, thank you very much. And let me ask another question about the modeling and control will play a significant role in the presented system and project. What do you think is the biggest challenge in modeling in such a system? How do they differ from the more traditional district heating networks?
Yeah, I guess I mentioned part of that. So we have cooling gains from the ground, and maybe if you choose the right operation scenario, you can also have heat gains from the ground to the pipe network, which you did not have in in later generations of the district heating. So because they were always insulated, right? High temperature difference to the ground, and now we're in a region where we're talking about network temperatures and ground temperatures on the same level. So for the model, it's important that you consider the ground capacity and then ground temperatures, so you don't have false results where you have infinite ground capacity, for example, something like that. So that we are trying to include in our model and then see what the MPC gives you as the optimum operation.
Thank you very much. And the last question to you, Simon. And what controls schemes are currently implemented to this complex energy system, and what schemes are planned for the future?
Yeah. So currently the system is using as a default option a rule-based control approach, where a lot of brain work went in. So they have like 120 operation scenarios where they say, okay, the weather forecast is predicting colder temperatures. We want to have some heat in the buffer storage and want to use waste heat or whatever, but it's rule-based and maybe not the optimum operation. What they're currently doing is implementing a MPC, model predictive control. Implementing it right now, but it does not consider the seasonal thermal energy storage because this is being built right now. So for interstores, we want to include this seasonal thermal energy storage, and then there's also the idea to see if reinforcement learning could also work for this kind of system, and what would be the trade-offs between implementing reinforcement learning and MPC.
Thank you very much. So we have a few minutes before the break, so let me ask at least two questions more. So my next question will be to Andrea Fratica from Rewitch. So the first question is, what are the peculiarities of the different cooling technologies proposed in the project?
Yeah, thank you for the question, Taras. So quite quickly, basically, as mentioned, we have three different technologies. I mean, the absorption one is mostly targeting the exploitation of very low grade heating source. Let's say we are targeting from 80 degrees C down to 70 degrees C. So basically exploiting very, let's say, low grade heat sources that cannot be used for any other application. While for the absorption ones, the target is to exploit a bit higher heating sources, around 90 to 100 degrees C. But the main difference is that with the hybrid absorption chiller, we can also cogenerate preheating for the process. So in a way, the system is providing at the same time cooling and heating to the plant, which is also most common application in many plants. And while the second one, the double evaporator solution, is exploiting higher temperature, but providing at the same time two different cooling levels. So in the end is giving more flexibility on the cooling side.
Thank you very much. So, and the next question is related to the comment I got from your presentation about the solar thermal technology application within the project. So how will this solar thermal technology will be exploited in the project itself?
Yeah, as mentioned, we did in the past other projects for industrial cooling applications. And in that cases, we were targeting the use of purely renewables, so purely solar thermal to drive the absorption technologies. And it turned out that the system is working from the technical point of view, but from the economic viability is basically impossible to come to reasonable return on investment. So the idea is to make a techno-economic assessment since the beginning of the project, trying to integrate the solar thermal inside the process to provide heating either directly to the sorption cooling system or to the process itself, but still keeping an eye on the overall cost of the system. So trying to make the integration as economically viable as possible, which means that we need also to profit of on-site waste heat sources in order to have the full system operating. So we are trying to make this assessment since the beginning, and is also, of course, considering all the constraints on site regarding the space availability for the installation of the solar thermal.
Okay, thank you very much.
You're
So, yeah, so for the time being, we finished our first section, and we finished it in time, almost, I would say. So thank you, everyone. Let's have a small break, a cup of coffee, and let's come back in 10 minutes. Yeah, waiting you all to continue. Thank you very much.
Thank you.
Thank you.
So the time break is finished, and I welcome everyone to continue our session. So the next thematical session is about methodologies, prototyping, and policy outlook of clean heat solutions. And I'm happy to present the next speaker, Vaishak Somasundaram from Geosyn project, with the topic presentation preliminary dynamic modeling of Geosyn high temperature heat pump and its application in rubber industry. Vaishak, the floor is yours, please.
Thank you, Taras. I hope my screen is visible.
Yes.
Myself, Vaishak, I am a postdoc fellow at University of Southern Denmark. I'm working in the Geosyn project. So the topic I am going to present today is the preliminary dynamic modeling of the Geosyn high temperature heat pump and its application in the rubber product industry. So these are the contents of my presentation. My colleague Lorenzo has already given an introduction to our project, which is Geosyn. So our objective is to integrate geothermal source having temperatures in the range of 140 degree centigrade to a heat pump as well as a heat powered refrigeration system. By heat pump, we are mainly focusing on high temperature heat pumps. And for this application, we are using water as the working fluid or the refrigerant, which is having better thermodynamic properties in terms of latent heat of vaporization, high critical temperature. And when compared to the other alternative, water exhibit higher performance at condensing temperatures above 150. This can be seen at the graph given at the below of this slide. Similarly, it has means it has no environmental impact or it is completely environmental friendly. However, these advantages of water comes with some limitations or challenges also. That is, water exhibits high pressure ratios as well as high discharge temperatures. In addition, they have low volumetric heating capacity, which means the compressors which are used for this application are bulky. Also, the other components. In addition to these two limitations, if our heat source temperature is less than 100 degrees centigrade, the evaporator of the heat pump will operate in vacuum, will cause additional challenges for the heat pump. So in the graph shown below here, one is how the COP of the heat pump, which is using water as the refrigerant, is varying. We can see that it is an excellent refrigerant for condensing temperatures above 150 degrees centigrade. Further, the volumetric heating capacity of the water also increases with increasing condensing temperature. As my colleague mentioned, we are developing a heat pump to demonstrate our idea. That is, the heat pump we are targeting to develop is having a capacity of 50 kilowatt and a 4-stage oil-filled reciprocating compressor is being developed by Dorin for this application. One of the main technological constraints which we are having here during the development of the system is that we need to limit the discharge temperature of the compressor below 270 degrees centigrade. In order to achieve that, we are providing an intercooling between two stages of compression, and the compressor which we are developing is having 4 stages, and we have came to these 4 stages based to limit the discharge temperature. In addition to that, in our basic configuration, we are having an internal heat exchanger at the section of the first stage in order to have required superheat as well as to avoid any liquid compression at the first stage of compressor. The system which we are developing is designed for an evaporator temperature of 120 degrees centigrade and a condensing temperature of 200 degrees centigrade. And our objective is to achieve a temperature lift of 80 Kelvin. So the heat pump which we are developing, we are targeting for applications where the temperature varies from 180 degree to 200 degrees centigrade. And these applications exist in industries which are related to food and beverages, textile, piping, chemicals and pharmaceuticals. In addition to that, industries which are related to rubber products, plastic, glass manufacturing, etc. The main working fluid or the heat transfer fluid which is generally used in these industries are steam. In addition to that, pressurized water and air are also being used. However, in some cases, they use thermal oil where accurate temperature control is required. So for the present study, we have selected a case where this here, the heat pump which we are developing can be used. That is, we are focusing on a rubber product manufacturing industry. In the slide here, the diagram on the right side shows the process flow diagram of a rubber product industry, where we can see there is a steam generating boiler which generates steam at 180 degrees 83 degrees centigrade at a pressure of 10.3 bar. That is, it produces almost saturated steam. The steam boiler input or the feed water or the condensate return temperature is at 103 degrees centigrade and it is heated to 183 degrees centigrade. The steam boiler presently uses heavy fuel oil as the heat source and it is having a capacity of 2.1 megawatt. Like any other industry, the steam which is produced at 183 degrees centigrade and 10.3 bar is then throttled for different applications. So in order to evaluate how our heat pump will fit in this scenario, we have developed a dynamic model of the heat pump in MATLAB Simulink platform. So a diagram of that model is shown here. We have implemented the required control strategies or the initial control strategies also in this model. So this model is being developed based on the nominal operating parameters of the heat exchangers as well as the compressor. That is, no dimensional parameters are used here. That is because our actual heat pump is under development. So whatever data which we are having currently is very limited. In addition, we have implemented the basic control strategies. I want to mention a few control strategies which we are using here. One is we are modulating the speed of the compressor according to the outlet sink temperature which is required. In this specific case, it is 183 degrees centigrade. In addition, the expansion valve, the opening of the expansion valve is modulated to control the superheat at the outlet of the evaporator. Further, there are 3 independent pumps which supplies the cooling liquid to the intercooler, and the flow rate through to this intercooler is also controlled so that we can have a definite superheat at outlet of each stage of compression, and thereby we can limit the discharge temperature below the 270 degree centigrade. These are the assumptions which we have adopted at present to develop this model. That is, we have considered an isentropic, volumetric and mechanical efficiency in the range of 75%, 85% and 95%. These are the best cases which are provided initially by our compressor manufacturer. The heat loss from whole components are neglected in this case. Pressure drop across the compressor, across the heat exchangers is assumed to be negligible. Presently, we have considered approximately around some 0.1 bar, 0.1 megapascal only, which is a rough assumption. And also, we have neglected any power consumption by the pumps, the auxiliary pumps which are involved in the system. And wall thermal masses of the heat exchanger is also not considered in this study. Further, in this model, we are having one dynamic input and all other inputs are steady state only. The main dynamic input is the geothermal source temperature, and the heat load of this model or the heat load to this model is assumed to be constant, that is around 2.1 megawatt. For the geothermal source temperature, we are monitoring the data of a geothermal well which is located, or a geothermal plant which is located at Tuscany, Italy. We are monitoring the source temperature at that well, and the data is recorded to our technology partner database, and it is available at our dashboard. So from this data, we have selected a suitable profile for this particular analysis. So that profile is shown in the first graph here, that is the geothermal source temperature. This is varying according to the time, and we have evaluated, or we have analyzed the performance of our heat pump for a 24 hours operation. So based on this geothermal profile, our evaporator pressure will be varying. However, the condensing temperature, condensing pressure as well as the sink outlet temperature is constant. And the objective of the heat pump is that it needs to provide a sink or it needs to provide steam at a constant outlet temperature. In this specific case, it is at 183 degrees centigrade. And as I mentioned earlier, this is achieved through modulating the speed of the compressor. And here we can see that for the dynamic varying input, we are able to maintain the sink outlet temperature as required. In addition to that, the required heat load or the heat of 2.1 megawatt is also achieved. During the operation, the COP of the heat pump is also being evaluated, and it is roughly observed to be around 3.5. Here in the same slide on the right side, how the control parameters are varied is also being shown. In the first graph where the discharge temperature is shown, we can observe that the discharge temperature is kept well below 270 degrees centigrade. So please note that this is based on the initial or the preliminary dynamic model. When we accurately estimate the pressure drops, also the efficiency of the compressors, this graph can have some changes in the behavior. Similarly, the degree of superheat on each stages is also shown here, and it is maintained well between 19.5 to 20.5. Further, we have also conducted some preliminary economic and environmental impact analysis also. Currently, this analysis is carried out by considering the scenario in Denmark, and we have selected a suitable electricity profile that is during the month of May. And the boiler efficiency is assumed to be 90%, and the other factors which are considered for this analysis is given here. This is the on the left side. It is a sample electricity profile for the month of May in Denmark. It can be observed that since the Denmark rely on mainly on wind, followed by solar for the electricity, during the daytime the cost of electricity is considerably low, or even it goes to negative. When we are comparing the operating cost with heat pump with that of a boiler, it can be observed for the baseline scenario, we are able to obtain a approximately 60% reduction in the operating cost. Now, if we in the present for the considered electricity profile, if we even increase the electricity cost by 20 or 40%, still the operating cost of the heat pump will be less than the baseline cost of the baseline operating cost of the boiler. It is very important to note here that currently we have considered a Denmark scenario, which relies mostly on the renewable energy sources. However, for countries which rely on natural gas or thermal power plants, the scenario will be different. For example, for countries like Italy and all, the operating cost of heat pump will be higher than the one which we are having for the Denmark. Similarly, we have also estimated the emissions from the expected emissions from the heat pump operation, as well as then comparing it with the boiler. For heat pump, we are expecting an approximately 80% reduction in emission. Same emission, the similar to the electricity operating cost. This low emission from the operation of the heat pump is due to the fact that Denmark relies mostly on the renewable energy sources. If the sources of energy is from thermal power plant and all, the emission factor for in such cases for electricity will be higher, and thereby the heat pump operating emission will be also be higher. So these are my conclusions. So under the simulated condition, we have observed that the proposed heat pump for the Geosin project, we can achieve a COP around some 3.5. We are expecting an operating cost reduction of up to 62% when compared to the conventional boilers, which are operating on the heavy fuel oil in this present case. And we are expecting a greenhouse gas emission reduction of up to 83% compared to the boiler system. So in the future work, we are focusing to calibrate the model, because here most of the assumptions are based on the initial guesses, and we are will be calibrating as well as validating this model based on our experimental test result. And in the further stage, the validated model will be used for the further virtual case studies which comes under our project. So we would like to acknowledge the fund received from the Horizon Europe grant. And this here we have shown the Geosin consortium, which involves 10 partners from different part of the Europe. So that is brief about our project. Thank you for your attention. If you have any question, I will be happy to take that at the end.
Thank you very much. Thank you very much, Vaishak, for the presentation. And let's move to the next speaker, Martina Battocchio from European Heat Pump Association. She will represent EU project GeoFlex Heat with the topic presentation, clean heat solution, market and policy outlook. Martina, the floor is yours, please.
Thank you for the introduction. Can you see my screen?
Yes.
Okay, just 1 second. I'm having is it full screen? No.
Now we don't have it. Please share it again.
Okay, wait.
Yes, now it's good. And show it within the slide. Full picture slide, please.
Mm-hmm. Okay.
Yes, okay. Please go ahead.
Thank you for the introduction and for giving me the opportunity to speak today. So I'm Martina Battocchio. I'm a EU projects officer at the European Heat Pump Association. But today I'm representing the GeoFlex Heat project as the dissemination, exploitation and communication leader, with this presentation on geothermal market uptake and policy outlook, and how GeoFlex Heat can identify itself in the geothermal landscape. So as some of my colleagues mentioned before, geothermal in Europe is at an inflection point. We have exploration and project pipelines that are growing, new technologies and cross-sector skills such as drilling and digital twins that reduce technical uncertainty. But we still have some barriers in place that do not allow this technology to fully develop, such as permitting, perceived seismic risks, and financial financing and funds. So here you can see the Europe geothermal pipeline map. EGEC, the European Geothermal Energy Council, has shared this visual in their market report in 2023. And I think that this map clearly shows how There is a lot of availability in terms of geothermal energy in Europe, in some areas more than others and with different levels of temperatures, but the source is there and it's ready to be fully utilized. Also here you can see geothermal heat reservoirs at European level. This visual is slightly older, it's dated 2013, but you can clearly see the source, the geothermal availability and the different depths at which it goes. And here you can see the growth of renewable energy generation from 2000 to 2022. So you can see hydropower, bioenergy, wind energy, geothermal energy, solar and marine energy. And you can also clearly see that geothermal contributes in a very, very small portion, especially compared to wind and solar energy. And this is because of the barriers that I mentioned before and the ones that I will go more in depth in the next slides. So from a policy outlook, I wanted to present what the EU and also national decision makers are doing and what they should do. So the European Commission and the European Union in general are supportive of geothermal energy. But we must not forget that implementation is national. So the countries need to remove the barriers and stimulate themselves what the EU signals are. For example, countries like Germany are moving to fast-track geothermal permitting and putting in place some scalability templates that will allow anyone who wants to fund or implement a geothermal project, a template that is ready and is harmonized. So as I mentioned now, what's needed now is to harmonize and make the rules more pragmatic and also target them towards de-risking finance and standardization for industrial applications. So the top policy levers to unlock this scale-up is, first of all, to permit streamlining and legal clarity, targeted public risk sharing, standardization and technical codes, and also community engagement and transparent monitoring. But in all of this, how does GeoFlexit map the market needs and addresses the policy barriers? So here you can see these three visuals. So the first one is a barrier. The second visual is what GeoFlexit is doing to remove those barriers. And the last one is the expected outcome. So the first barrier that I wanted to present is the high exploration and technical risk that reduce bankability. And what GeoFlexit is doing is producing a fully documented open access system simulator that models geothermal flow assurance, grid pricing, and this is combined also with a techno-economic strategy to analyze the multi-variable techno-economic scenarios. This reduces investor uncertainty by producing repeatable, transparent modeling of revenue streams and sensitivities. And the outcome is that lenders and investors can run site-specific scenarios, incorporating local electricity and heat prices and operational profiles, moving projects from an idea from speculative to bankable. And this directly answers the call for demonstrable de-risking tools. The second barrier is the scaling of mineral deposits on heat exchangers that reduce recoverable heat and increases operational and maintenance costs. So what GeoFlex is doing to address this barrier is a combined heat pipe heat exchanger with a scaling reactor that lowers reinjection temperature safely and at the same time accelerates controlled scaling so minerals can be harvested. And the outcome is that there is a lower maintenance, a higher extraction efficiency, new revenue from recovered minerals, which all reduces the operational and management risk, and also improves payback periods for projects that work with high mineral brines. This makes previously marginal resources attractive and directly increases the exploitable resource base. The third barrier is the lack of flexible heat supply and integration into industrial processes. And GeoFlex Heat develops and validates a high temperature heat pump to lift geothermal heat to industrial temperature, and also a steam accumulator to buffer variable demand. And the containerized skids allow modular deployment at industrial sites. And the outcome is that demonstrating that geothermal combined with a high temperature heat pump combined with an underground thermal energy storage system configuration can meet industrial heat profiles, materially reduces market risks, and also support procurement and industrial policy levels. The next barrier is the permitting fragmentation and the lack of standardized demo data. So what GeoFlex is doing is standardization and policy work to provide standardized policy-ready documentation and policy demonstrators data, which helps regulators to create a harmonized permit procedure and reduce the time to approve industrial replication. We have another barrier that is social acceptance and local opposition. So what some partners in GeoFlex are doing is develop a social acceptance guide and a life cycle assessment document to clear site level life cycle assessment results and provide a tested social acceptance playbook to reduce the probability of community stopping conflicts. And then we have the limited commercialization and intellectual property pathway for innovators. And for this, we are developing an exploitation and intellectual property strategy so that we have containerized, we basically package prototypes into containerized skids, validated business cases, and an IP management route. So that the project increases the private sector willingness to invest and scale up production. So that being said, what could be concrete policy asks to ask to policymakers? So the first one is to implement one-stop permit procedures and fixed review timelines for demonstrators and industrial geothermal. The second one is about creating national or EU blended fund instruments to co-finance drilling and containerized demo deployment. The third one is about supporting standardization and a replication pathway by funding standard test protocols and a standardization roundtable for containerized geothermal modules. And the last but not least is to mandate transparent monitoring and community engagement by requiring environmental baseline data, real-time monitoring, and community participatory processes for geothermal demos. So as stakeholders, what we can do to make sure that we can shape Euro's clean heat future and make our voice heard is we can do that by participating in European Commission calls for evidence and public consultations. We can engage through working groups and the Have Your Say platform. We can provide insights as an expert via stakeholder advisory boards in European projects. Now, most European projects foresee this type of advisory boards, and joining also the Clean Heat Industry Group that connects policy and industry voices. And this is something, for example, that we are doing at the European Heat Pump Association. So if you want to know more about it, I left the link here in the name of the group. And this is all from my side. If you want to know more about GeoFlexHeat as a project, what we are doing, what our goals, or you want to participate by being part of our stakeholder advisory board, feel free to reach out to me. You have my contact here, or to the GeoFlexHeat project coordinator, Professor Usam Huara from Brunel University of London. Thank you very much for your attention.
Thank you very much, Martina, for the great presentation. Okay, so next move with the next speaker. I'm delighted to present the next speaker from Vito. Virginia will represent Project Urgent with the presentation topic, Geothermal Exploration Solution for Urban Context, Sustainable and Affordable Urban Geothermal Exploration, Novel Technologies and Workflows. Virginia, the floor is yours, please.
Thank you very much for the introduction. So indeed, I will present to you the Urgent project on behalf of the Urgent Consortium. And I'm very happy to be here today because I listened to all the previous presentation and I see that for most of them, it's somehow a given that the resource is there. But in fact, in most geothermal projects, you sometimes face some issues while finding the resource and the geothermal resource. And that's what we are aiming for in Urgent. It's really to improve geothermal exploration techniques. And we are particularly targeting urban and noisy industrial environment, which fits pretty well with different talks that have been given. So what were our main motivation? Why did we start with the Urgent project? Basically, we all need, and I don't need to convince you that Europe needs solution to decarbonize its heating sector. And we agree that geothermal energy offers a very good and alternative solution to fossil fuels for heating building, but also for feeding in some industrial processes. So here we also had the feeling that in urban areas, geothermal heat can be used to feed in existing and future district heating networks. It can be, but in such a case, it means that also the geothermal source has to be quite close to the demand because you want to minimize pipeline costs, but also minimize heat losses. Finally, or not finally, but one of the other motivation was really because as it was mentioned in the previous presentation, geothermal is quite often associated with high pre-drilling risks. So we need definitely to de-risk geothermal energy deployment. And for that, what is quite often used at the exploration stage is seismic. And it is quite critical for identifying geothermal reservoirs and assessing hydrothermal resource potential. And this is particularly true in complex geological settings that we find quite commonly in Europe. But at the moment, there is still quite limited or lack of knowledge about geothermal resources, and there are still some challenges when you talk about seismic exploration in urban areas. And why is that so? I don't know if you have witnessed some geothermal exploration campaign in cities, but when you come with big seismic trucks, it is sometimes very difficult to access part of the city, and it's also quite disturbing sometimes for the population. The final motivation was also that when you get non-optimal or insufficient data quality at the reservoir level, this can really hamper identification of faults and reservoir characteristics. And the lack of precision and knowledge about fractures and faults will have some impact on the drilling risks, but also on financial risks. And it is quite linked as well on induced seismicity risk, because when you don't know where you can find fractures and faults, then you might not know where seismicity could be initiated, for example. And this, of course, has some impact and affects societal engagement and public engagement and public acceptance, sorry. So who are we? We are a team of 8 partners across 5 European countries, and we bring in together 3 test sites where we want to test new technologies that have been developed or are being developed for seismic acquisition, mainly for urban areas and industrial and noisy areas. So we are a bunch of researchers, but also we have software developers and industrial partners. I won't go into all the details because I don't have much time, but this is our team. And today it won't be really a technical presentation such as the one that you saw for some of the other projects, but I want to rather give you an overview of the activities we do in Urgent and why do we do them. So the different objectives we have, first of all, we have the objective, as said, to develop innovative technologies and workflow for seismic exploration of geothermal resources. But we have also 5 specific objectives. The first one being linked to the innovative acquisition technologies. So we want to enable low impact, affordable, high quality seismic data acquisition to de-risk geothermal development in key underexplored areas. And by that, I mean also urban areas. We also want to have efficient data analysis, so to have faster data analysis to improve reservoir characterization and fault detection to increase drilling success rates. We want to be able to also have some impact on the risk management of geothermal projects by applying advanced modeling and simulation to ensure sustainable long-term reservoir performance and risk management. And when I say risk here, I mean mainly induced seismicity risks. We also want to have some impact and some objective linked to social engagement, environmental performance, and market uptake of the technologies that will be developed. So we want to strengthen community acceptance, to have good overview of the environmental performance of the 2 technology and especially of the exploration stage of geothermal deployment. And we want to make sure that the technology will be adopted later on. And finally, the real outcome of the project in terms of technical aspect is to come up with some integrated exploration workflow. So we want to work on all the different steps of geothermal exploration using seismic technologies. So as said, the project is still in its initial phase, I would say. We have basically 3 main steps. So first of all, we have the step 1, which is linked to the technological software and method development and survey design, because we want to test the technologies while performing real test studies on site and real test surveys. So we have at this stage still the design of the campaigns to be realized. And then the step 2 would be really the validation of the technology and the methods while enhancing social engagement and market uptake. And the final stage will be the integration of the results and the definition of the exploration strategies. So I will not go into the detail, but just to give you a glimpse of what we want to achieve. So here, when it comes to the design and development of novel exploration technology, Urgent aims to develop innovative miniaturized micro-electromechanical systems called MEMS, based nodal seismic sensor. And these MEMS would be integrated into autonomous recording nodes. And with that, we want to achieve high quality and low cost deployment of seismic receivers. So here you just have a figure showing you what the nodes will look like. And also what is quite important, I guess, for the people who at least are in the exploration sector, is to see where do we want to position the nodes that will be developed within Urgent. So we want to have lightweight, but also high quality control. At this stage, the nodes are being manufactured and they will be tested in the workshop in November, beginning November. In addition, and in parallel to the development of the nodes, in Urgent, we want to develop an electric low impact seismic source, so-called the eVibe. That source can emit repeatable and low distortion acoustic signals over a broad frequency range. And this is to be able to reach and to image deep geothermal reservoir with a very high accuracy. Again, so here it's just a prototype of what the carrier of the source will look like. It is being manufactured and will be tested together with the nodes beginning of November. At the end of the project, so we will have 20 kilonewton eVibe and around 700 nodes developed. And these will be tested at the 3 test sites. In addition to that, I said we want to also work on how to optimize survey designs. So what can we do to reduce the exploration cost? So you can, what could you optimize in terms of deployment of sensor, of shot points? And for that, we have a partner, RTS, working specifically on these aspects. So far, they have used data that have been acquired at the Vito site last year, so 3D seismic data, to test some workflows to optimize and to understand how you could reduce, for example, the number of sensors to be deployed. So at this stage, RTS is still at the finalizing, let's say, the survey design for 2 of the sites, and the Vito site, where we will have a 3D small-scale acquisition, will be finalized a bit later. But the idea is to have 2 campaigns where we would acquire 2D seismic lines, so one in Poland and one in Hungary. So one is in a more or less urban context, and the other one is more on a sensitive industrial site where there is a refinery, and we want to prove that the technology developed won't be too impactful. And we want to use compressive sensing and adaptive sampling to enable efficient imaging across the subsurface. Then there is a risk management toolbox that is being developed. The goal is to maximize heat recovery while minimizing induced seismicity. So this product is developed by Vito and AGH. So it's a Polish partner we have. And at this stage, we have a minimal viable product of the toolbox that is available on the Git of Vito. So the toolbox is designed as a simulation and optimization platform for THM. So it's a thermal hydromechanical models and easily parallelized to reduce the computational costs of optimized simulator agnostic and build a modular architecture. So basically what it does, it gives you the best location to position your wells for a given project, knowing the position of faults, for example, and telling you what distance you should be from the fault, what would be the optimal position and also architecture of your well in order to have the best outcome in terms of heat, but also to make sure that you would not trigger any seismicity. And in parallel to that, we have a partner working on the development of AI and ML-driven algorithm for efficient post-processing and improved fault detection. So it's DGB, and they are working mainly on the improvement of the existing OpenDetect machine learning software, where they really start from the processed seismic data and make the and help to interpret the data. And they work mainly on two different projects. They develop an interactive machine learning driven workflow to facilitate interpretation of faults and horizons. And at the same time, they are working on the training of a foundational model to predict faults and horizon via the interactive workflow. At this stage, so this is still at the, we are still working on that, so it's ongoing work. But I hope that if there is a next event organized, I will be able to really focus, or actually the partners could even present themselves the status of these different aspects. And then finally, and that's my final slide, we do work also, of course, on social engagement, looking at community acceptance for urgent concepts, and also looking at what are the next steps so that we have a market uptake of the urgent concept. And I think that with that, I will stop my presentation because I will be over time. Thank you very much for your attention.
Thank you very much, Virginia. It was indeed insightful. And yeah, we have two more presentations meanwhile within our current session before the Q&A. So let's move to the next speaker. Happy to present Eloy Alvarez and Daniel Alias from LATAT. They will represent the project Geostasis with the topic LCA and SLCA methodology definition for decarbonization projects in industries. Please, gentlemen, the floor is yours.
Are you able to see my screen?
Yes, we do.
Yes. Okay, perfect. So hello, everyone. So we're involved in this Geostasis project that our colleague Angel has explained about it before. I'm on the task of developing the life cycle assessment and the social life cycle assessment of this Geostasis project together with Daniel. He's not able to join today, but I will explain you the different parts of this presentation. So I will do an explanation of what's a life cycle assessment, an environmental one, and also what's a social life cycle assessment, giving examples of how it works, for example, in a geothermal context. Also, what's the purpose of the life cycle assessment and the social life cycle assessment in relation to geothermal energy. The third aspect that I will explain is the application of this life cycle assessment in the Geostasis project, how we are collecting the data, in which way, and how we're going to conduct the modeling of this project, the life cycle assessment. And finally, I will do some explanation about the forecast results. So the life cycle assessment is a process to assess the environmental impacts of a product or activity over its life cycle. So to provide a little bit of context, with the Geostasis project that searches to implement a geothermal system of conveyor belts in a factory, a life cycle assessment of a geothermal system would consider all the environmental impacts associated with this technology, from raw material extraction, manufacturing, processing, the transport, the distribution, also the use of this geothermal system, the maintenance, and the impacts associated with the end of life. So all these different phases are considered within an environmental life cycle assessment, and they have inputs and outputs as it can be electricity, materials, or waste. All these inputs and outputs also have environmental impacts, and the results of the environmental life cycle assessment are the final outputs of these impacts. Once the environmental impacts are calculated through the environmental life cycle assessment, it's possible to detect hotspots that, we see that which impacts are high or are low, and we detect these different hotspots. And then we develop strategies in order to mitigate these hotspots. And to describe a bit, give some characteristics, we can say that it's a robust tool for assessing environmental impacts, because it's also reliable, because it's based on ISO standards, and the databases have constantly quality checks. It's also consistent, and its results are credible, and it has also assumptions and uncertainties, but it's reliable. And in order to conduct this environmental life cycle assessment, there are 4 different steps. First, it's the goal and scope definition, where the plan of the whole analysis is defined. Then a life cycle inventory, where we gather all the data of all the elements in the energy system from the different partners involved. Finally, we model it with a tool called CIMA Pro. So we introduce all the data that we gathered in the life cycle inventory in the CIMA Pro tool with different processes, and we model it in order to acquire these impacts, environmental impacts. Then there is also a social life cycle assessment. This type of assessment is a methodology to acquire the social impacts of products across their life cycle. The social LCA framework has a stakeholder approach, because the impacts are considered on different stakeholders, and these impacts may affect them in a negative or a positive way. Taking the geothermal technology again as an example, there is extraction of raw materials, processing, manufacturing, transport, as I have explained before. And all these different stages have impacts on the stakeholders. That these stakeholders are workers, local communities, society, value chain actors, and consumers. And all of them are considered within a social life cycle assessment. And how do we measure these impacts? So through social indicators that are based on a CIRCA methodology. In the case of the GeoStakes project, we've conducted a workshop in order to refine all the indicators that this methodology provides, and just value the ones that are considered to be most relevant in order to obtain the impacts associated with the stakeholders. So this life cycle assessment and social life cycle assessment has as a purpose so detect, evaluate environmental and social impacts. So in this way, we can detect different hotspots based on the results. From these hotspots, there are improvement actions that can be elaborated. In the GeoStakes project, for instance, results will be results that we have that are from these hotspots. We will develop improvement strategies in order to mitigate these hotspots through a mitigation strategy. And finally, this analysis can guide policy recommendations, and in the GeoStakes project are expected to influence policy by the development of a roadmap. The final objective of developing this LCA and social LCA is the decarbonization of industries based on geothermal energy technologies, and these analyses are supported by sustainability goals. So here in this slide, I will explain you how this environmental life cycle assessment and social life cycle assessment is applied in the particular case of the geostaircase project. So there is the common factory that produces conveyor belts, and we are going to conduct the life cycle assessment of this factory, but it's related to energy. Therefore, we're all, and this is the functional unit, 1 kilowatt hour of heat delivered to the user, a geothermal system to provide 3,250 megawatt hour for the industrial production of conveyor belts over a minimum service life of 30 years. So in the analysis, we'll consider the elements related to energy. So we don't consider the machines, for example, related to the production of conveyor belts. And all these elements related to energy, we evaluate its impacts from raw material extraction until disposal. So all the lifespan. And the analysis is to compare the factory as it is right now to a future geostaircase scenario with the geothermal source to see how the environmental impact changes, and if it is a positive thing to implement this geothermal system. So as you can see on the screen, the baseline scenario, that's the current factory right now. We have the heating system, the cooling system, and the electricity as three different systems. And in the geostaircase scenario, the same. The cooling system will remain with the same characteristics, and the heating and electricity systems will change because the geothermal technology will be introduced in this comparison. For the moment, we have just modeled the baseline scenario. As you can see, the three systems, they are also divided. We have modeled them divided in three different sections: construction, use, and end of life. The heating system has construction. For example, we have modeled the boilers, the natural gas tank, and other elements that are within this construction. Also, the use phase is, for example, the burning of natural gas, the transport of the oil that is used within the factory. The end of life currently in Kauman in the heating system is the valorization of oil. So we model all this in a SIMA Pro tool. Also, the electricity is electricity that comes from the grid. And the cooling system, some example of construction can be the pools that have been constructed for cooling the system. They use the water, that tap water, and the end of life, it's wastewater. And the results after modeling all this with the SIMA Pro tool can be 16 environmental impact categories following the PEF recommendations. And in the social aspects, social impacts tied to CILCA indicators for worker, local communities, society, value chain actors, and consumers, and are expressed in risk levels in the end. And that's it. Thank you very much for listening. And well, I would like to ask you if you could, I've seen that some projects maybe are also conducting this type of life cycle assessment. So if we could connect, share knowledge and information in order to improve our assessments, that would be great. So you can contact me over this QR code in LinkedIn or through email. Thank you so much.
Thank you very much for the presentation. And yeah, let's finish our thematic session number 2 with the final presentation from Krzysztof Banasiak from SINTEF, who will represent the project geothesis with the presentation topic, the geothesis prototype of industrial heating and cooling. Krzysztof, the floor is yours.
Can you see my presentation right now?
Yes, we do.
Perfect. Yeah, so very briefly, meaning delivering the technical details on the geostaircase solution. As mentioned before, what we do, we want to support the existing manufacturing place that has some, let's say, need for utilities, hot oil, hot thermal oil at around 180, 185 degrees Celsius, and cooling needs supporting pretty much the cooling system at around 20 degrees Celsius. And what we can use for those purposes is a geothermal source, which, as mentioned before, will not be harvested as such in the project. It would be only simulated, but nevertheless, we need to develop the system that would be harvesting the 90 or 85 degrees Celsius geothermal source, and maybe if necessary or if possible, using the additional shallow geothermal heat sink at around 20-25 degrees Celsius. Why we do that? As mentioned, to demonstrate that the clean heat technology can be useful, can be efficient, and can be scalable. If it is scalable, we do believe that we have some good candidates throughout industry. And if you follow the diagram here, it's mostly pulp and paper. If you follow the value of the needs at around 200 degrees Celsius, it's the biggest chunk of the needs in that type of industry is exactly within this temperature range, which is what we want to deliver here. That something, that thermal system, we hope to have it quite compact, quite modular, meaning possible to scale up and down if necessary. We do want to operate still below 200 degrees Celsius, which for now is a kind of a nice border if you follow the technology development. Many different systems or technologies promise delivering heat at 200 degrees Celsius, not too many above 200 degrees Celsius. We also hit the limit more or less. And what we want to do, we want to integrate as much as possible those two cycles, meaning heat pump cycle and the thermally driven ejector cycle, which is supposed to produce the air conditioning. We evaluated to deliver, to meet those goals, we evaluated 3 different options. Option ABC, option A, the least integrated version, but as you can see, the least troublesome and the cheapest, the option that consumed the least capex, based on a 4-stage vapor steam compression supported by thermally driven ejector cycle. At that stage, we evaluated butane. Option B, kind of the same, but we elevated the evaporating conditions in the steam cycle, and by doing so, we needed to provide some additional temperature increment, meaning that the butane cycle becomes not only the thermally driven ejector cycle, but also a classic vapor compression cycle. And option C, purely water-based or steam-based cycle, fully integrated with thermally driven ejector loop. Those 3 options were evaluated, first of all, in terms of not only energy efficiency, but let's say technical maturity, but also costs involved, because we have our own budget limitations, so we needed to evaluate how much everything would cost. And as you can see the values here, this is what we have initially planned for: 100 kilowatt in terms of the heat pump, and 25 kilowatt in terms of the ejector-based system. And this is by the way, the cap we had in our budget. And as you can see, it's much more. And in addition to the cost evaluation, we have performed, let's say, a kind of ranking based on many different criteria: economic criteria, thermodynamic criteria, technical criteria, safety criteria, awarding pluses for those systems or those aspects that we do believe are quite profitable or technically sound, or minuses for those aspects that we do believe might cause some problems or expenses in terms of finances. And once we have calculated all those different pluses and minuses, it turned out that all the systems will be challenging. But nevertheless, it's option A, meaning a nice combination of steam-based cycle with steam-based heat pump, combined with butane or propane, in other words, hydrocarbon-based ejector cycle. That solution most likely should be followed. Going to the details of the system, we have decided for option, which is, as mentioned to you, option A. When it comes to the heat pump, we figure out that the only viable option would be going with 4-stage vapor compression performed in a oil-free 4-stage open-type piston compressor. That has some implications. I mean, selection of the technology, selection of the working fluid has some implications, like, for example, the quite complex or troublesome warm-up procedure and a shutdown procedure, which would have to be performed with air. Or, last but not least, the necessity of desuperheating after each compression stage, which we want to resolve by, I would say, quite a nice solution where we would like to use gravity-driven auxiliary evaporators that would do the desuperheating job for us. And in principle, they do not require any control. That's one advantage. Another advantage is that by desuperheating to the condenser, we increase the COP of the cycle. And if we talk about COP, according to our expectations in the nominal operating conditions, meaning lifting temperature from, let's say, 90, 95 towards 180, 185, so around 100 degrees Celsius when we take into account the auxiliary loops, the COP should be around 3, slightly below 3. When it comes to the next cycle, which is propane refrigeration cycle, I say propane because on the way we evaluated that it's pretty much the same in terms of complexity and COP. But for our partners, project partners, company manufacturing heat pumps, hydrocarbon-based heat pumps, it's much easier to work with propane. Then we said, okay, let's go for propane. It changes not so much and brings some other benefits. Then it's in the end the propane refrigeration cycle, which is heat-driven, supported by ejectors, of course, a pump and 2 ejectors. Why 2 ejectors? Because we figure out that for the conditions given, meaning if we have like 90 degrees Celsius geothermal water, we want to produce 20 degrees Celsius utility, and we need to take into account the ambient conditions at around 40 degrees Celsius. There's no way the whole cycle should run with only 1 compression stage in the ejector. We need to go with 2 stages of compression, meaning that the ejectors would have to be connected in series. And that's the solution. And as you can see, the ejectors were evaluated with the use of a CFD tool we have maybe not created, but upgraded for the needs of the project. So what we plan to do, we truly hope that before we press the button and run, we will have the chance to test both units, both installations in our Syntab lab. And once we have figured out all those most likely happening tiny imperfections and refining the system, both units would be installed at the test site, which is common manufacturing place. And this is where we also want to launch the system to perform real duty operation. That's the plan for us in technical perspective. Thank you very much for your attention.
Thank you very much, Krzysztof, for the presentation. And yeah, we are happy to finalize our latest presentation for the time being for this thematical session number 2. I hope audience had enjoyed the presentations from our speakers, and propose to move forward with the Q&A session. So we've got several questions from the audience, and I'm happy to start with the first one. So the question from John Ashbridge to the urgent project Virginia. So why is the urgent only considering seismic data from subsurface imaging? And yeah, so basically he mentioned that his company is the first to utilize airborne fault tensor gradiometry for geothermal exploration in Europe. Yeah, please comment on that.
Yeah, thank you very much for the question. I have made just a small reply in the chat. But so why did we focus on seismic? First of all, because it is the technique that is mostly used in sedimentary contexts in Europe, and also because it is useful, especially when you look at not super high temperature geothermal resources, and it also provides a good resolution, or it can, if you do your campaign correctly, a good resolution in terms of fault and fracture imaging. And as I said, I think it's quite crucial, these features, not only for seismic risk reduction, but also because sometimes these faults and barriers can really enhance the flow and the flow circulation in your reservoir. And okay, to be very also clear, we know that it would be good, and it's often very useful when you combine different techniques. But in urgent, we thought that with the budget we had as well, it was better to focus only on seismic and to do as much as we could on this specific technology, rather than to start adding up many different techniques and not to go into the details. So we agree that it's nice if we can combine also other techniques, that's for sure. But we still believe that seismic is very useful, especially once you have selected a site and you want to look into the detail of this site in order not to miss any critical fractures or faults.
Thank you very much, Virginia, for the for the answer. Okay, and we have the second question in the chat. So the question is addressed to, I believe, Eloy Alvarez or Daniel Elias from Geostasis. Not looking at LCA aspects of electricity from the grid, isn't that the risk for steering towards lower LCA effects of heat and cold at the cost of rising LCA effect in the E-system? So I hope you might answer that.
But we are taking, we're looking at electricity from the grid, actually in the LCA.
Okay.
So yeah, what the diagram that you saw is that we are considering well, we have all the data from Kaman factory, how many electricity they consume every year. So in our LCA, we model it in, well, electricity from the grid in Spain. We are also aware that there's renewable energy coming from solar panels, but we don't introduce this input as electricity because we consider it as no CO2 is emitted, but yet we consider the impacts of the construction of the solar panels in the infrastructure construction.
Thank you very much. And we have two more questions to you, Eloy, within our next questions. So are the technologies and tools developed in the geothesis applicable to scenarios with a heat source other than geothermal?
Sorry, can you repeat the question?
Yeah. Are the technologies and tools developed in geothesis project applicable to the scenarios within the heat source other than geothermal?
Well, for the moment, we are analyzing the scenario without geothermal energy and the one with geothermal energy. So it's the one that we are considering, but yeah, with the CIMA Pro modeling tool, you can model different types of electricity energy sources, because it's a standardized database that integrates many processes that are available to model different energy sources.
Thank you very much. And I believe the next question is addressed to Mr. Pardinas from the same project. What challenges do you expect to face when integrating geostasis technologies at the demo site or any pilot?
Hey, hello. So in the end, I mean, well, whenever you are not starting a process from scratch, integrating technologies into a system that already exists, that's already running, and so on, can be challenging. And this is the case for us. With the heat pump that was presented right now by my colleague Christoph, in the end, we are only meeting partially the demands in the factory. That meaning that, we will need to install it and to prepare everything for the install in parallel to the current boilers whenever there is a stop in the process. So in the end, that will be a challenge by itself. Of course, it happens the same with all the implementation of sensors, implementation of the digitalization we are doing there. We cannot disrupt the process. If not, the colleague, the partner in the project is not happy. It costs a lot.
Okay, thank you very much. And the last question available to our speakers is addressed to Martina Patocchio from GeoFlex Heat. Where do heat pumps come in when we talk about geothermal?
Thank you for the question. I think this question has been addressed extensively by all the presentations today, or pretty much all of them. But as a representative of the European Heat Pump Association, I'm happy to reply. So it's pretty clear that heat pumps are the bridge between geothermal resources and heat demand, because while geothermal systems provide an amazing, stable, renewable heat source, the temperature often doesn't directly match what industries, buildings, or district networks need. So heat pumps upgrade that heat to useful temperature levels, making geothermal flexible and more widely usable, I would say. So combining geothermal with heat pumps can multiply the usable heat output and drastically improve also system efficiency. From a policy standpoint, this hybrid approach allows geothermal to contribute more meaningfully to decarbonizing heating, which is still Europe's largest source of emissions. In our project, GeoFlex Heat, we are demonstrating exactly this, the fact that high temperature heat pumps can lift geothermal heat to industrial levels, store it, and then deliver it flexibly. So I would say that heat pumps aren't just complementary, they are essential to unlocking the full potential of geothermal energy for both industry and district heating uses. Thank you.
Thank you very much. Yeah, and it was inspiring, and hopefully now our audience is more informed and aware how we might accelerate our efforts within the various technology implemented in one project. Yeah, so I hope our audience is happy within the presentation provided, and I wish everyone a great end of the day. And meanwhile, I'll be asking to open the cameras to have the final screen within our presenters as well as audience to make the final common screen together. Meanwhile, thank you everyone and wish you all the best.
Thank you very much.
Thank you.
Thank you.
Thank you.
Yeah, have a great day to everyone.
Bye.
Thank you. Bye.
Thank you. Have a good day.
Bye-bye.
Bye-bye.
Bye.